Friction is a force that opposes relative motion between systems in contact. We're going to look at some dry friction here, which is friction between these two dry surfaces that are in contact. And if you look at what's going on close in as they're in contact there, as one tries to move with respect to another, there's roughness on these surfaces. And not only is there roughness, but there's actually attractive forces between molecules making up the two objects as well. So even for very smooth surfaces, there's going to be friction forces here. And as you try to move, you can see there's going to be bumpiness as you move, and that's going to act to oppose any motion along that surface. You can see here that for small normal forces, there's going to be a certain amount in contact, and as you push down further and harder, you're going to have more of the surface in contact. And so you're going to have more friction forces opposing your direction of motion. This is why if we sit on this crate, now it's harder to push the crate. Whereas if we're not sitting on the crate, it's easier to slide the crate. Obviously, it's also harder to push because there's more mass you're trying to push. But imagine trying to push that mass on a frictionless surface. You would be able to move it with the person sitting on it. It would just move slower, right? But it wouldn't be harder to overcome the friction. Whereas with friction, that additional weight means additional normal force, means that the surfaces are closer together, there's more contact area there, and you have more friction opposing the direction of motion. In friction, let's say we have a box here, we're pushing on it with some force F, and then there's some friction force opposing it. You have weight acting down and normal force acting up. You're going to see some behavior like this as we increase the force we're pushing with. So we'll take you through this plot here as we consider first static friction. This is where the box is not moving yet. With static friction, our force of friction is always less than or equal to some mu s times the normal force. And this mu s is the coefficient of static friction. And that tells you how hard friction is working, essentially. And we'll look at that some more in just a little bit. So this is a property of the two surfaces that are interacting. So the wood on the steel or whatever it is, those two surfaces determine what that coefficient of static friction is. And then that times the normal force gives you what your static frictional force can be. This works up until you reach what that maximum allowable force is. And so this is static friction. As long as it's not moving, this will be true. So you push harder and harder, your input force gets harder and harder, and the static frictional force just matches that at any point. So here, the static frictional force is just always equal to whatever that input force that is trying to make it move is. And it stays equal to that up until you reach some maximum value where there's not enough friction anymore to be able to keep it from moving. And this point is called impending motion. And that's where you have the maximum static friction force that's equal to mu Sn, that is the most it can do, right? So that's the right before it starts to move, that's how much friction force you have. And then after you push a little bit more than that, it starts moving. And once it's moving, it's generally a little bit easier to keep moving because the objects are moving with respect to one another. So there's less friction force there. And you get kinetic friction at this point. And the force of kinetic friction, we're going to model with this mu kn, where that mu k is, again, a coefficient that depends on the surfaces involved. But here now we call it the coefficient of kinetic friction. And that'll stay true for as long as it's moving. Now, this is a model. As things heat up, these coefficients can change. So the model is good for when the model is good for, right? But assuming that it's not heating up, assuming that we can use these coefficients and that's how it's behaving, then this will be true. So if you think about brake pads and trying to clamp down on something and that heats up, that's going to change your properties, right? So you have to use some slightly more complicated models to deal with that take into account the temperature dependence of that process. One way of remembering this, if you want to remember F equals mu n, is that my force of friction F is equal to mu n, or fun, F-U-N. Now that works great if you don't speak Greek. If you do, the mu is like an m sound, like the letter M. So it's more like m. So if either of those help you either fun or fun, go for it. Here are some coefficients of static and kinetic friction for various surface-surface interactions. Remember, both surfaces matter for this. So wood on wood, you get a static friction coefficient of about 0.5 and a kinetic friction coefficient of about 0.3. For some, you can get pretty high, and in fact, for some, you can get over 1. So these are all dimensionless because it's a ratio of the normal force to the frictional force. Or it's actually the frictional force over the normal force is the coefficient of friction here. So it can be over 1, and in that case, like aluminum on aluminum, if you try and push the aluminum, you actually need to put in more force to slide the aluminum along the surface than it would take to pick up the aluminum off of the surface.